There is a particular kind of unease that settles over an observatory when the mathematics refuse to cooperate. Not the drama of a sudden discovery, but the slow accumulating realization that something in the data will not resolve. On July 1, 25, the Atlas Survey telescope in Rio Hurtado, Chile, reported a faint streak to the Minor Planet Center, a routine detection that quickly became anything but routine. Pre-discovery observations were soon located in archival images, extending back to June 14, 2025, from multiple Atlas facilities worldwide and Caltech's Zwicky Transient facility. Within days, orbital calculations confirmed what the velocity and trajectory had already whispered. This was not a member of our solar system. It was given the designation 3 Atlas, the third interstellar object ever detected passing through our cosmic neighborhood, following on Mdima Muamua in 2017 and Tuitiba Borisov in 2019. But as the months passed and measurements accumulated across telescopes from Hubble to the James Webb Space Telescope, a subtle discomfort began to spread through the community. The orbit would not settle. Astrometry is the discipline of measuring positions in the sky with extraordinary precision. When you observe an object against the background stars, you are essentially asking, where is it now? And where will it be next? For a purely gravitational trajectory, an object responding only to the sun's pull and the gentle perturbations of planets, the answer should converge. The residuals, those small differences between predicted and observed positions, should scatter randomly, shrinking as your model improves. But with 3I Atlas, the residuals did not behave like noise. They persisted. They clustered. They suggested, with quiet insistence, that something else was influencing the object's path. The measurements hinted at a small, continuous force, an acceleration beyond gravity measured at approximately 5.9 HO10 astronomical units per day squared. Yet, the usual signatures that accompany such forces remained faint, inconsistent, or absent altogether. This is not a mystery of identity. We know what it is: an interstellar comet, a fragment of some distant planetary system, now passing through ours at approximately 130,000 miles per hour. The mystery is one of cause. What mechanism can move an object through space without leaving the expected physical receipts? If you enjoy this unfolding investigation, subscribe for more Beyond the Solar Veil cosmic documentaries. Modern orbital tracking is a process of relentless refinement. Telescopes across the globe acquire images, often nights apart, each frame carefully calibrated against known star positions. Software compares the object's location to predictions generated by increasingly sophisticated models. Gravitational effects from the Sun, Jupiter, Saturn, even the inner planets, are folded into the equations. If the model is complete, the residuals, those stubborn differences, should diminish with each new observation, scattering symmetrically around zero. But with 3I Atlas, the pattern was different. The residuals did not vanish. Instead, they exhibited structure, small but systematic offsets, drifting slightly with time, recurring in ways that randomness cannot explain. This is the signature of unmodeled physics. Something is acting on the object that the gravitational solution does not account for. In the language of celestial mechanics, this is described by introducing non-gravitational parameters, terms that represent forces other than gravity. For comets, this is routine. As ice sublimates near the sun, gas jets off the surface, producing a recoil that gently alters the trajectory. The mathematics of this are well understood. You fit the non-gravitational terms to the data, adjust your predictions, and the orbit stabilizes. But here is where the discomfort deepens. Fitting the acceleration is straightforward. Proving its physical source is not. The non-gravitational signature in 3 Atlas is measurable, particularly near its perihelion on October 29, 2025, at 11:44 UTC, when it reached its closest approach to the Sun at 1.36 astronomical units, roughly 126 million miles, moving at its maximum speed of 68 kilometers per second. Wide signal. The sky says something is pushing. The object spectrum tells a more complicated story. When an icy body begins to outgas, it leaves unmistakable traces. Ultraviolet invisible spectrometers search for the cyan radical, the dissociation product of hydrogen cyanide, which glows in a characteristic band near 388 nanometers. Infrared instruments look for water vapor proxies, or the thermal signature of warming ice. Sub-millimeter radio arrays hunt for carbon monoxide and carbon dioxide, molecules that can sublimate far from the sun where water remains frozen. Dust reflects sunlight, creating a coma, a diffuse cloud surrounding the nucleus, and sometimes a tail, pressure-driven or ion-driven, depending on particle size and solar wind coupling. These are the expected receipts for a comet under acceleration. Yet, with 3I Atlas, the chemical portrait was profoundly unusual. When NASA's James Webb Space Telescope turned its near-infrared spectrograph toward the comet on August 6, 2025, it revealed something unexpected, a coma dominated not by water, but by carbon dioxide. The CO-Idaho ratio measured 7.6 to 0.3, approximately 18 times larger than expected for its heliocentric distance, and 4.5 standard deviations away from the trend line established by previously observed comets. This is not a subtle difference. This is a comet that should not exist, not in this form, not with this chemistry. Several explanations remain plausible, each grounded in known physics, but all requiring conditions at the edge of what we have observed. The surface may be depleted of water ice, either through prolonged cosmic ray exposure during its interstellar journey, estimated at roughly 800 million years based on galactic trajectory analysis, or extreme galactic cosmic ray processing could have selectively destroyed water ice while preserving more stable, cone ices deeper within the nucleus. A thin, non-volatile crust may have formed, insulating deeper volatiles and restricting outgassing to small localized vents. The grain size distribution might be skewed toward larger particles, detected in observations showing dust mass loss rates varying between 0.3 and 4.2 kilograms per second. Activity could be confined to specific regions that only become active under precise geometries. None of these possibilities are exotic. All have analogs in solar system comets, but collectively they introduce a profound uncertainty. The chemical silence where we expected a chorus does not rule out outgassing. It simply removes the easiest, most direct confirmation. And so the nervousness grows, not because the data suggests something impossible, but because it refuses to settle into clarity. Heliocentric distance is one of the most important variables in cometary physics. As an object approaches the sun, the intensity of solar radiation increases dramatically, proportional to the inverse square of the distance. At roughly 1 astronomical unit, the Earth-Sun distance, the heating rate crosses critical thresholds for water ice sublimation. Inside this boundary, volatile activity typically accelerates. Brightness increases. Coma density rises. Dust production intensifies. This is the predictable choreography of a comet awakening. But with 3 Atlas, the timeline felt misaligned. NASA's Hubble Space Telescope captured the comet on July 21, 2025, when it was 277 million miles from Earth, revealing a teardrop-shaped cocoon of dust. As the comet descended toward perihelion, brightness variations and morphological features appeared in the data. NASA's MAVEN spacecraft at Mars detected hydrogen atoms surrounding the coma on September 28, 2025. The Mars Reconnaissance Orbiter's HiRISE camera observed it from 18.6 million miles on October 2. Even the Perseverance rover paused its exploration to photograph the visitor on October 4. But these observations did not align cleanly with when the orbital solution required the strongest non-gravitational acceleration. It was as if cause and effect were sliding past each other, separated by a phase lag that the simplest models could not explain. Thermal inertia offers one possible mechanism. If the surface has low conductivity, heat deposited by sunlight does not penetrate quickly. The interior warms slowly, lagging behind the external heating curve. Subsurface volatiles may not sublimate immediately upon crossing a distance threshold. Instead, they respond hours, days, or even weeks later, once the thermal wave has propagated inward. Outgassing driven by this delayed heating would not peak at perihelion, but offset from it, creating a temporal mismatch between position and activity. Another possibility involves structural failure. A thin crust can withstand rising internal pressure only up to a point. If that threshold is crossed suddenly, after gradual, silent heating, the object might vent in a brief intense episode, visible as a brightness spike, but hard to connect to the smooth, continuous acceleration that the orbit seems to demand. The comet's rotation period, measured at 16.16 hours, adds another layer of complexity, as different faces rotate into and out of sunlight on a predictable cycle, yet the acceleration persists beyond what simple rotational jets would produce. Porous structure complicates the picture further. Gases generated deep within the nucleus must navigate a tortuous path to the surface, diffusing through cracks, pores, and voids. This internal flow is neither immediate nor uniform. It can produce an effective delay between solar input and visible output, a decoupling of energy and ejection that makes interpretation difficult. The result is an object that does not behave like a textbook comet. It accelerates, but without sustained brightness surges proportional to the force. It shows chemical activity, but the chemistry is inverted, carbon dioxide where water should dominate. It crosses a critical distance threshold, but its response feels muted, intermittent, offset in time. By mid-December 2025, S3I Atlas made its closest approach to Earth at approximately 170 million miles. 1.8 astronomical units. On December 19th, multiple facilities turned their instruments toward the receding visitor. Hubble reobserved it on November 30 with the Wide Field Camera 3. The NASA SOHO mission caught glimpses between October 15-26. Even spacecraft never intended for comet observation joined the campaign. NASA's Europa Clipper, en route to Jupiter, captured 3A Atlas from 164 million kilometers on November 6, 2025. And the Psyche spacecraft tracked it over 8 hours on September 8-9. The mystery tightens around a single uncomfortable question. What kind of system produces a measurable push without leaving proportional chemical evidence in the expected form? Dynamical anomalies come in several forms, each with its own physical origin and observational signature. Asymmetric outgassing is the most common culprit. When gas jets preferentially in one direction, due to rotation, topography, or uneven heating, the nucleus experiences a recoil force. This is the classic rocket effect, measured directly in solar system comets like 67P Churyumov-Gerasimenko by the Rosetta mission. But it requires gas. If the spectroscopic evidence shows unusual chemistry rather than abundant volatiles, invoking standard outgassing recoil becomes less satisfying. Dust-driven momentum transfer is another candidate. Micron-sized grains, accelerated by sublimating gas, carry momentum away from the nucleus. If dust production is sustained, the cumulative effect can alter the orbit. But this mechanism depends on the dust-to-gas ratio, grain size distribution, and ejection velocity, all of which are difficult to constrain. Moreover, dust produces scattering, and scattering should be visible. NASA's SphereX Observatory collected data for approximately 1 week in August 2025, providing additional constraints on the dust environment. Yet the coma remains subtle compared to the dynamical signature. Fragmentation introduces a different kind of acceleration. If the nucleus splits, shedding fragments or large particles, the center of mass shifts. This can mimic a non-gravitational force in astrometric data, especially if the fragments are faint and go undetected. Several interstellar objects and long-period comets have exhibited splitting events, sometimes without obvious precursors. Observers scrutinized 3 Atlas for such features across multiple wavelengths. Hubble's continuing observations through November 2025 allowed astronomers to refine the nucleus size estimate, placing an upper limit at 3.5 miles, 5.6 kilometers, in diameter, though it could be as small as 1444 feet, or 440 meters across. Some images showed marginal hints of asymmetry, but nothing definitive. The possibility remains open, but unconfirmed. Radiation pressure, acting on small particles in a coma or tail, can also influence the apparent position of the object. If the photocenter, the brightness-weighted centroid, drifts due to asymmetric dust distribution, astrometric measurements may report a position that does not correspond to the true nucleus. This is an instrumental effect, a measurement complication rather than a physical acceleration. But it can produce residuals that look disturbingly similar to real non-gravitational forces. Here is the source of the scientific unease. Multiple mechanisms can produce similar signals in the data. This is called degeneracy, and it is one of the most frustrating aspects of remote observation. You see the effect, the orbit won't settle. But isolating the cause requires additional information that is often not available. You need spectroscopy across multiple epochs and geometries, but the target is faint and moving. You need resolved imaging to detect coma structure or fragments, but the angular size is tiny. You need time series photometry spanning the entire apparition, but observing time is precious and competed for fiercely. Each dataset narrows the possibilities but rarely excludes all but one. And so the community is left with an uncomfortable menu. Several plausible explanations, none fully satisfying, each requiring assumptions that remain difficult to verify independently. The object does not exist in isolation. It moves through a dynamic, structured environment, the heliosphere, the extended magnetic domain of the Sun, shaped by the solar wind and punctuated by current sheets, shocks, and pressure fronts. The solar wind is not constant. It fluctuates with solar activity, with coronal mass ejections, with the 11-year solar cycle. As 3I, Atlas descended through the inner solar system during the rising phase of solar cycle 25, it encountered varying plasma densities, changing magnetic field orientations, and shifts in the ultraviolet radiation environment. These conditions affect how dust and gas behave once they leave the nucleus. Charged grains can be deflected by magnetic fields. Plasma interactions can ionize molecules, producing emission lines visible in spectra. Velt's X-shooter spectrograph observations reveal detailed spectral features, including a surprisingly red reflectance spectrum in the visible range, but also altering their trajectories in ways that complicate coma morphology. The solar wind itself exerts pressure, small but measurable at the scales of cometary particles, and this pressure varies with distance and time. Jupiter, though still distant, casts a long gravitational shadow that cannot be ignored. 3I, Atlas is currently headed toward a close flyby of Jupiter scheduled for March 2026, and even at its current distance, the giant planet's gravitational influence subtly perturbs the trajectory. These perturbations are well modeled in principle, but they depend on precise knowledge of the object's mass, velocity, and approach geometry. Small uncertainties in any of these parameters propagate forward, widening the cone of possible future positions. Moreover, if the object has a coma, even a faint one, the effective cross-section for solar radiation pressure increases. Jupiter's gravity pulls on the nucleus, radiation pressure pushes on the coma. The result is a complex coupled system where the observed photocenter may not move exactly as the bare nucleus would. Observers must disentangle these effects, separating real acceleration from apparent motion, physical forces from measurement artifacts. This is not a failure of science. It is the reality of working at the edge of detection, where every measurement carries uncertainty, and every interpretation depends on assumptions that cannot always be tested. What makes an object nervous-making is not its strangeness, but its resistance to simplification. If 3I Atlas were a clean, textbook interstellar comet, bright coma, strong water emission, well-behaved orbit, it would still be fascinating, a messenger from another star. But it would not be unsettling. The discomfort comes from the mismatch. The orbit says persistent, non-gravitational acceleration. The GWSD spectrum says extreme coma dominance with minimal water. The morphology says activity is present, but subtle and geometry dependent. And the timeline says the causal sequence doesn't align with standard sublimation models. None of these observations violate known physics. Water ice and carbon dioxide. Ice have different sublimation temperatures. Thermal lag is real. Crust formation happens. Cosmic ray processing over hundreds of millions of years can alter surface chemistry. But together, they resist collapsing into a single, satisfying narrative. Scientists are trained to seek parsimony, the simplest model that fits the data. Here, no simple model fits cleanly. Every explanation requires caveats, auxiliary assumptions, appeals to unusual but not impossible conditions. And so the unease persists, not because the object is alien in origin, though it demonstrably is, but because it behaves in ways that test the boundaries of our predictive confidence. What would resolve the mystery? The answer is straightforward, though increasingly difficult as the comet recedes. More data, of higher quality, covering a broader range of conditions and geometries. Consistent spectroscopy across the outbound leg would clarify whether the COMU dominance persists or evolves as heliocentric distance increases. Long baseline astrometry extending into 2026 and beyond would allow the non-gravitational acceleration to be characterized with greater precision, distinguishing between steady, impulsive, and episodic forces. High-resolution imaging from space-based platforms could reveal subtle coma asymmetries, jets, or secondary condensations that ground-based telescopes cannot resolve. Mid-infrared observations from WST at larger distances could detect carbon monoxide, which sublimates much farther from the sun than water, providing an independent check on volatile composition. Polarimetry of scattered light would constrain dust grain properties, whether they are compact or fluffy, silicate-rich or carbonaceous, offering clues about formation conditions in the Birth Nebula. And sustained monitoring through 2026, as the object recedes beyond Mars's orbit, would reveal whether the acceleration continues, weakens, or ceases, answering whether the effect is purely thermal, rotation-modulated, or something more persistent. But opportunities are finite. Interstellar objects move quickly on hyperbolic trajectories. They do not return. Atlas will depart our solar system permanently after its Jupiter encounter, heading back into the cold depths of interstellar space at 68 kilometers per second relative to the Sun. The observing window narrows with each passing week. By the time the community fully recognized the chemical and dynamical anomalies, the comet was already past perihelion, already fading, already climbing back out of the inner solar system, where only the most sensitive instruments can track it. Some observations were attempted and succeeded. Sabaru Telescope in Japan captured detailed observations on December 25, 2025, and the Breakthrough Listen project even searched for artificial radio signals during the closest approach, finding none. But the dataset remains incomplete, the picture still fragmented by the practical limitations of telescope time, weather, and instrument sensitivity. This is the reality of studying visitors from other stars. We see them briefly, we measure what we can, and then they are gone. The nervousness, then, is not about fear. It is about humility. It is the recognition that our models, however sophisticated, are built on assumptions calibrated to solar system conditions, comets that formed in our disk, processed by our sun's radiation over billions of years, interacting with our particular heliospheric environment. 3. Atlas formed elsewhere, around a different star, in a protoplanetary disk with potentially different chemical abundances, temperature profiles, and radiation histories. It spent perhaps 800 million years drifting through the interstellar medium, bombarded by galactic cosmic rays at intensities and energies our solar system objects never experience. It carries with it chemistry and structure shaped by processes we can model, but have never directly observed. And when such an object arrives, moving too fast for comprehensive study, exhibiting acceleration without proportional conventional signatures, it exposes gaps in our understanding that we did not know existed. It is the acknowledgement that precision and certainty are not the same thing, that you can measure an orbit to within kilometers, constrain a Ka-Heo ratio to 7.6/0.3, estimate a nucleus diameter between 440 meters and 5.6 kilometers, and still not 0.6 kilometers, and still not know, with confidence, what physical mechanism dominates the non-gravitational force at any given moment. The solar system, even our own, is not fully mapped. The physics of small, distant, rapidly evolving volatile bodies is not a closed book. And when an object arrives from beyond, carrying with it the chemistry and dynamics of another star's debris, it brings questions that our instruments are only beginning to learn how to answer. This is why unanswered questions matter. Not because they promise sensational revelations or hint at impossible explanations, but because they sharpen our methods, refine our models, challenge our assumptions, and remind us how much of the cosmos still operates at the edge of what we can measure, predict, and understand. 3i. Atlas will not return. Its hyperbolic trajectory carries it outward at escape velocity, back into the vast interstellar night, where it will drift for tens of millions of years before encountering the gravitational influence of another star. But the data remains, archived in observatories across the globe and in orbit. The residuals remain, documented in astrometric databases and orbital fitting residuals. The chemical measurements remain, preserved in spectroscopic archives from JWST, Spherix, Bell-T, and dozens of other facilities. And the quiet, patient work of interpretation continues, one model refinement at a time, one cross-check at a time, until the next interstellar visitor arrives, perhaps in a year, perhaps in a decade, and we try again, better prepared, more experienced, but still fundamentally humbled by the messengers from the stars.